for a timeliness. All right, well, let's get started. Everybody, welcome to the first spring 2024 seminar of the CFEM UBS AI and Data Research Series. I'm really happy to have Joseph Simonian today. He's going to talk about the complementary roles of data science and econometrics in model validation. So I'm really happy to have Joseph here because he is someone who really, throughout his career, has bridged the gap between theory and practice. After a PhD at UC Santa Barbara, he's had an illustrious career in quant finance, including companies like Natixis, Fidelity, JP Morgan, PIMCO, Lehman Brothers. So he's been in really practicing quant finance for about 20 years now. And he's also an editor at the Journal of Financial Data Science, at the Journal of Portfolio Management, and his current role is as a senior investment strategist at Scientific Beta. So very happy to have Joseph Simonian here. And if you have any questions, please feel free to put them in the Q&A. And without further ado, let's get started.
Thank you, Sasha. Welcome, everyone. So the topic of my talk, as Sasha mentioned, is the complementary roles of data science and econometrics in model validation. And I think this topic speaks to two important aspects of what quants really are facing today. One is the issue of model validation, which is an age-old problem really on Wall Street. And if you ask me, model validation is probably the most important aspect of any investment process. If you think about a financial product, it's just like designing any other product, right? And you don't want to use it unless you know that it's been tested properly and it's appropriate for whatever particular use you have for it. But oftentimes what we see on Wall Street, unfortunately, are products that are released out to the public that have really been vetted only with rudimentary back tests and really no effort to really subject their products or the strategies to really robust testing. And something I'll speak to later, but I can just get it out there now. If we really want to make finance into a more scientific enterprise, which is really what finance has been trying to do for, I would say, at least half a century, right? So, finance has had a lot of science envy, if you will. But unfortunately, even though it's had all this science envy, and you all have heard about a lot of proponents of fit models from physics or chemistry or what have you in finance, despite all of that fervent excitement over those types of applications, what we haven't done really is apply the scientific method, right? And I think before we start and look at the slides and go into the topic in detail, let's just review what a scientist would do if they had a theory. And our investment strategies are our equivalents, our analogs of theories, okay? So if a scientist has a theory, what they'll do is they'll typically say, okay, I have a theory, it makes logical sense, I've got some basic experiments that validate its use, and hopefully its predictive efficacy, but let me subject it to more rigorous testing, right? And science has its own ways of doing that. And the whole attempt in model validation in natural science is to try to falsify a theory, to really break that theory. And if you can't do that, then there's some evidence or good evidence that that theory actually says something about the natural world and can be used to make predictions and so on. In finance, what we often see is the opposite approach, where a investment team will notice some empirical regularities. They may do some rudimentary back testing and say, okay, and run a bunch of tests where they get often false positives and say, oh, eureka, we've discovered some genius, great investment strategy. And then what happens is, I'm simplifying a little bit, but you get the picture. What happens is when they productionalize that model and they make it into an investment product, then when reality hits, in other words, data that the model has not been subjected to, then what happens is it fails and it underperforms. And oftentimes these products get shut down, so on and so forth, or get heavily revised and they go back to the drawing board, in essence. That's one of the reasons why the quantitative investing is actually hard to do. Not that fundamental investing is easy, but a quant process is not just opening a textbook and picking out your favorite model and then running it and making millions of dollars. And actually, to do it well, you really have to approach it like a craftsman, right? And really refine whatever model you're working on and subject it to these rigorous tests, right, that I mentioned, to make it more scientific. So that's sort of, I set the table here now for why model validation is important and some of the failings you see on the street. Now, data science and econometrics, traditionally have occupied, in statistics itself, two separate buckets, if you will, of data analysis. And we'll talk about that in a second. But, all of you have been privy to the prevalence now in the last few years of data science and machine learning on Wall Street. We started the Journal of Financial Data Science in 2019. Frank Fabozzi, Marcos Lopez de Prado, and I were the founding co-editors. And we did it because for years, the three of us had been seeing, much more prevalent use of data science and machine learning models on the street. And we thought that there should be a journal where people could share ideas and actually go through peer review, because finance is not like other sciences, as we know, and I'll talk about in more detail. It's somewhat unique in terms of its data and the sources of its data. And for that reason, we thought the journal was appropriate. And it's been going 5 years strong now. And but we're still at a place now on Wall Street where there are many that are confused, I would say rightfully so, about the appropriate roles of traditional statistics and econometrics and machine learning and data science in finance in general, but model validation specifically. And so I've classified, the different types into three buckets. The reactionaries, who are traditional quants. They're often from, physics or math backgrounds, and who they may pay lip service to machine learning and data science because, it's sort of a cool thing to talk about nowadays. But in reality, they don't really believe in it for various reasons, which we'll talk about. And then we have the revolutionaries, right? So you see there are several hedge funds out there now, usually smaller hedge funds, that have built their investment processes from the ground up. And when you talk to some of the leadership, what they'll tell you is, they really don't have any bandwidth for traditional statistical models. They're really committed to driving their processes through machine learning. And then you have what I call the ecumenicals, which they draw on different aspects of both that are useful. And I would consider myself an ecumenical, but I've actually gone a little bit farther in my own research. And at the end of the presentation, I'm going to discuss a framework that I've developed and I've published. I think the link is in the chat now, called modular machine learning, where you actually use traditional econometrics and machine learning in the same process, and each occupies its own role and module. That's why, hence the name, in order to effectively validate models. So we'll talk about that, and we'll have some Q&A and where you guys can ask me questions. And I think Sasha will be peppering me with questions as we go along, as he sees fit. So, this topic is not new. We're in 2024, and Leo Breiman, who, if you don't know, he's one of the inventors of random forest, which is a very popular algorithm, both within and without finance. And Breiman wrote a paper in 2001 where he actually talks about what he calls the two statistical cultures. And he came about this paper because what he had done is, I think he taught at UC Berkeley, I believe, for a number of years. And then he left academia and he went and he worked as a consultant in the private sector. And what he found as a consultant in the private sector was the way that his clients were approaching data and statistics in terms of what they prioritized, what they felt was important, was very different from what academic statistics had taught him for decades. And so eventually, I guess he balanced both worlds, but he came back and he started to do some academic research again. And in 2001, he had this paper about the two statistical cultures. And the first culture is the data modeling culture, which has been the dominant tradition in statistics. And it's really the main concern is to provide information about the relationship that exists between input and response variables. And it assumes that underlying whatever empirical data you're looking at, there is some sort of data generating process. So if any of the audience is familiar with philosophy of science, they're realists about about natural or economic entities, right? They actually believe that what you are measuring is actually there. And the job of statistics is to uncover and discover what the actual relationships are between input and response variables, and to figure out, if you will, what that process is, what those mechanics are. The data modeling culture, which obviously started in just traditional statistics, also has been borrowed by econometrics very heavily. And if you go by the great debates that happened when econometrics was being founded, there were individuals like Tal and Koopman, right? So if you look at the Cowles Commission, which is an old economics commission that was founded at Yale University, there were big debates at the time about what direction should econometrics go in. And Koopman and his ilk, like Havelmo, they really felt that econometrics should really be founded upon traditional statistics and really rely on theory. This was opposed to another group that were working at the National Bureau of Economic Research in Cambridge. I'm in Boston, so it's right by me. And these individuals were much more concerned with empirical measurement and prediction, right? They were less theoretically bound. And this tug of war went on for a long time. Eventually, even though you had some outliers like Milton Friedman, in economics and econometrics, eventually the dominant tradition became this theoretically oriented data modeling culture, okay? And that's why, and we'll talk about this later, many of the most popular econometric models are useful for certain things, but they're actually very bad at other things, but they have been purposed for both, right? Because they have been essentially part of this tradition of the data modeling culture, which is assumed that when a model is accepted on its theoretical merits, it can be used for various things like prediction, which we found is not the case. Now, in contrast, the algorithmic modeling culture assumes that the relationships between inputs and response variables are way too complicated to actually discover or uncover for ourselves. So our main concern in statistics and econometrics, by extension, should be to just make successful predictions, okay? So I mentioned Friedman. Friedman had a very famous paper that was ignored at the time. It only became famous decades later, where he essentially articulated what's in philosophy of science is called an instrumentalist approach to theories. And Friedman was not the first person to come up with this, but he may have been among the first in economics to talk about this. And his view was, I just need theories to help me make predictions. They're tools for organizing the file cabinet of data that I have. He didn't really view that theories were telling you anything real about the economic world, right? He basically thought that I have a theory, it makes sense on the surface, and it helps make predictions. That's enough. In philosophy of science, that's called instrumentalism, where you don't actually imbue any realistic properties to your theory. You don't pretend that any theory is telling you anything about the world. All you care about is making forecasts. And if the theory can help you do that, then you accept it, right? So this is a debate that's been going on for a long time in philosophy of science. And so the algorithmic modeling approach, which is what machine learning and data science really are founded upon, is much less theoretical, right? It's much more based on heuristics, rules of thumb. Now, there is some theory that goes into it. Obviously, it doesn't completely violate every probabilistic law that we've accepted, but it's much more amenable to ad hoc methods versus traditional statistics. And if you want evidence of that, this goes through the history a little bit, this slide about Enber and Friedman and Koopman. But if you want evidence of that, just think about standard OLS regression. Think about all the rules and all the easy ways you can violate an OLS regression, right? Think about all the assumptions, independence of errors, linearity, right? Et cetera, normality assumption. There's so many assumptions in a very simple model, and it's because it is very theoretically rooted. I'm not saying that as anything bad necessarily, But that's the drawback. Now, what is the good side of theory? The good part of theory is that when you have so many rules, like in a regression, that when your model is broken, you have to go back to the drawing board, right? So, okay, you have a bunch of factors, right? Input, explanatory variables that are correlated to a too high a degree. So you get a multicollinearity error, right? Let's say in whatever code you're running. Okay, that tells you this is not going to fly because there's too much linear correlation, at least between these factors. You got to go back and rerun it. In many machine learning algorithms, you don't get those kinds of errors. You can actually throw anything you want into it and get an output. So there's a light side and a dark side to theory, if you will. But the point here, the takeaway, is that the algorithmic culture is much less reliant on theory, and that's where machine learning and data science get their bearings and foundation from. And then there's a theoretical side to statistics, where traditional econometrics really is born from. And that's why there's this clash. Okay. Now, let me get to one of the main points here. Traditionally, what we find is that traditional econometrics are very good at explaining the past. Okay. So if I asked you, what were the economic drivers of the energy crisis in the late 70s, or the massive inflation in the late 70s? You could run a vector auto regression and tell me, here were the drivers and here were the, and basically just be a traditional econometric breakdown, but the machinery is there to give me a fairly thorough statistical and economic explanation for, why inflation was driven up in the late 70s, or perhaps after this inflationary period, what drove inflation here. So it's very good at explaining the past, not so good at explaining the future. So there are very famous or well-known models, econometric models like regime switching models, which are very good at cutting up the world. And I'm going to use that later in the framework that I show you. But they are very bad at predicting the future. And if you don't take my word for it, there's been decades of research on this by illustrious names like Bob Engel, who have actually talked about this quite a bit. And I ended up writing a paper in the Journal of Financial Data Science called Minsky versus Machine: New Foundations for Quant Macro Investing. It's kind of a pretentious title, but the whole point of that paper was that we acknowledge that regime switching models are very prevalent on the street, but nobody really uses them to manage money, right? Because their predictive record is very poor. And so in that paper, we develop a machine learning approach to regime switching and actually present some trading models that show you how to use our framework to do the same job that a traditional regime switching model does, at least on the predictive front, which is essentially classifying macroeconomic regimes and then investing based on those classifications and predictions, right? So that's what traditional econometrics is very good at. In contrast, data science and machine learning are much better at prediction, but not so good, in my experience, at explaining the past. And that is one of the reasons why they are not in favor, or some quants, let's call them old school quants, let's call them, are not really in favor of data science and machine learning approaches, because sometimes the output is you can't really trace the output one for one all the way back to the inputs. In other words, there's some opacity to that model. Think about a deep learning model, right? There are hidden layers, and often it's impossible, if you have a complicated model, to actually trace exactly how everything happened and why, and so on and so forth. There's inputs, and then there's an output, and that output may be very useful. We have a very good predictive track record, but it doesn't necessarily lend itself to explanation. And that can be a problem, because on Wall Street, we have clients, we have internal stakeholders, senior management, and they often want to know, how did you get the result you got, and can you replicate it? In some environments like banks, there are actually regulations that require you to replicate output to a certain extent. I don't know how the regulations have changed recently, but banks are typically much more stringent than, let's say, asset managers in that respect. But even within an asset management firm or a hedge fund, if you're an analyst and your senior PM asks you for a model, you build it, it's got a great track record predictively. Maybe you run a pilot fund and it does well and so on. But then you're going to be asked, well, how did you get that result? And anybody on Wall Street who's been doing this for a long time is going to want some economic explanation for it. And with some machine learning models, those explanations are a little bit harder to provide than others, and certainly usually harder to provide than traditional statistical or econometric models. So the question that's in front of us now is, are they mutually exclusive? Well, before we get to, at the end, I'm going to give you the modular machine learning framework, as I say. I'll answer the question for you now. I don't think so, because I can tell you that whenever I start any kind of a research project, let's say I want to build a new trading strategy or what have you, right? What I would do is start with a regression, because it's something that I know inside and out, dealt with it for a long time. Everything's explainable, everything's understandable. And I think I've always thought that it's a good test to test out your ideas on a simple model. And if it makes sense there, then you can actually process that information, the inputs, on a more sophisticated model. But if it breaks down within a simple model, then for me, often it's kind of like I stop and I say, well, what's wrong with this thing? Think about it. If you define, look at the traditional definition of a factor model, for example. A factor model has to be a parsimonious set of independent factors. Parsimonious means relatively small, and independent means usually linearly independent. Okay, so if the inputs, the factors, or machine learning speak, the features that you throw into your regression fail on that front. In other words, if your model needs 55 factors to produce a R square of 0.05, that's the parsimonious test, that fails. And then if you have a bunch of multicollinearity errors jumping up, that to me is a model that screams for revision and editing, right? So an OLS regression is always a good place, I think, to start any kind of a study. But then often you find that you need to go a step further, because in markets, of course, we have nonlinear relationships, we have interaction effects, and so on. Now, interaction effects and nonlinears can be also captured with certain kinds of regression. But as I've written publicly in articles before, the mathematical effort that it often takes to get those models going is often not worth the effort than going to more data science-driven algorithms that are a little bit more sparse, if you will, and a little bit more efficient, at least mathematically, for my taste. And they do capture those nonlinearities and interaction effects. So that's another topic we can talk in depth about in the Q&A. But
Joseph, I have a quick question about this. So you talk about these sort of two big schools of thought as with regards to data in finance. Mm-hmm. How does optimization fit into this? Because I know that optimization is often used in data science as a way to train an algorithm, and there are ways to control for bias and lots of things in that area. But also when we think of Markowitz or more classical methods that sort of work with econometrics, we're also talking about optimization. So do you think, is that sort of maybe the glue that keeps it all together, or what? How do you think of optimization as it fits into these two big sort of schools of thought?
I think optimization is a little bit outside that debate, right? But I think it can work in both realms. And with optimization, you have other kinds of concerns, right? So, if you use gradient-based methods, for example, you often get stuck in a local optimum, right? So there's, global optima that can be used to sort of address that problem. Some of those are actually machine learning or data science driven, like genetic algorithms, which are old hat now, but these are sort of global optimization frameworks that can be used to kind of resolve those issues. But I would actually, so I think optimization is a little bit agnostic to this debate. It's kind of, you can use it in both realms for different purposes. And most importantly, optimization doesn't speak to the forecasting or prediction issue, right? Optimization is typically used to derive weights on things, right? Once let's say you've selected your stocks, right, if you will, it can actually tell you what weights to give them. Mm-hmm. But in other words, on an active management basis, to tell you what to invest in, you need some kind of forecasting model, and optimization doesn't enter into the picture there. But so that's my response there. I think in terms of I don't know if you want to talk about the Markowitz model in general, but I mean the mean variance optimization itself for 1953, good idea. Markowitz actually edited one of my, I actually edited one of Markowitz's papers, one of his last papers, where he thanked us at the end, the co-editors. So I have a lot of esteem for him. I think since then there's been a lot of developments, in mathematics and just finance that obviously make a straight use of that model potentially unsuitable right now, but in 2024. But the basic idea that you have to look at the risk that you're undertaking for the return that you expect, that has not left finance. So in that sense, it was a wonderful and novel idea relative to, this is a little off topic, but just give me 10 seconds on this. Before that, the old way of investing was the sort of Graham and Dodd way, right? Which was essentially, I don't mean the value investing side of it. I mean the idea that your portfolio is 10 stocks that you really like and you've done due diligence on them and there's no effort to diversify. It's just, I know these are good companies. That's the way Warren Buffett and Charlie Munger invested for decades with a lot of success. So I'm not besmirching that approach either. But that's to give you an idea, the Markowitz revolution, if you will, or the MPT, modern portfolio theory revolution, was really based on this idea that, hey, maybe there's another way of investing where we don't try to stock pick and have these such concentrated portfolios, but actually have risk play a front and center role in how we build portfolios. That was the idea, right? It was sort of a response that would have come before. So now model validation, I have so I mentioned this in the intro, but I'm just, you have the bullets here, but it's worth repeating. So this is, I don't hear this a lot on the street, but I mean, it's really a mantra that I live by a lot. Because again, I've been on the street for 20 years, right? So I've been in every kind of quant team that you can imagine, and I've seen some really good processes, some brilliant folks, and people who are craftsmen. That's a good word, right? So much more important than intelligence is, do you view this as if you were building a table, right? That's what really a quantitative strategy is, right? It's building a piece of furniture. You have to be a craftsman. You have to make sure that all the legs are even, that it doesn't wobble, that you can throw things on it, put heavy things on, it doesn't collapse under its weight, right? So model validation is a big part of that. And, I think the whole idea that we have science envy, but that immediately leads us to using differential equations and, everything else under the sun. But we haven't thought about the fundamental way of scientists, how they do their work, which is trying to falsify their theories, right? Instead, we have a lot of this false positive, overfitted, simple backtest only, inception point bias kinds of strategies that eventually ultimately fail in practice. So I think this is an important, no matter how you do validation, my advice would be to please do some real model validation. It's very important. So now, statistical multiculturalism, this is my term, right? Because what I've done is I've said, instead of just being an ecumenical where you say, okay, we've got a couple projects going on. One of them we're doing with, a traditional vector autoregression or whatever it is. And the other one we're doing with machine learning. The idea is, can you actually combine these two in a single framework? And is there any reason to do so? That's the most important thing. So when you do anything in whether it's research or in any kind of endeavor, any walk of life, my belief is that you don't do it just for the sake of doing it or building something pretty. Is there a reason for you to do it, right? And I'm not talking about art. I'm talking about, sort of science or, more practical endeavors. And so the question is, does using traditional econometrics help solve a problem for us as quant, as investors, that machine learning doesn't in a model validation process? And it turns out it does. So any of you have done what's called cross-validation. If you don't, I'll tell you what it is in a second. May have discovered that it's not necessarily ready-made for finance. How is that? So what is cross-validation? Cross-validation is you say, okay, look, I have a large expansive sample of data, and I'm going to split it up into different subsamples. They're called folds in machine learning and data science. And some of these folds, this is a simplified version of it, I'm going to use to train my model. And some of these other subsamples, these other folds, I'm going to use to test them. Now, in our business, you would use what's called time series cross-validation, right? Which means that your training and testing has to proceed chronologically, because in finance, unlike some other sciences, you can't use the future data to predict the past, right? It doesn't make sense to us because our data has memory, right? Okay. So in other words, if you see a price for a stock today, that price reflects to some degree the headlines, the earnings releases, et cetera, that have come before it, and would be cheating in the most egregious way to actually use future data to help us predict the past and then say, oh, we've got some wonderful strategy. Okay, so even if you use time series cross-validation, I've got a question, and I'll answer for you. How do you choose the folds? What is the criteria that you would use to decide how many folds, where you cut the folds? Traditional data science does not give us that information because traditional data science comes from a natural science origin. In other words, computer scientists who do data science and machine learning are typically not concerned with financial data. Okay, so I think somebody's raising their hand. Isn't it? I think it's better if we have the Q&A written into the comments, and I'll address each of the questions at the end. That's right?
Yeah.
Okay. So please do that. So we don't really have any clue as to how to split those folds up. But remember regime switching, which I criticized earlier? That framework by itself gives us a ready-made tool to actually cut the world up into folds. So you say, look, I don't know how to split this data. I've got data from 1980 to 2024. In that sample, I know, because I lived through it, I've got inflationary periods, I've got disinflationary periods, but I don't know exactly when those periods started, right? So you can actually run a regime switching model, assume that inflation is your process in a simple version, right? And you will be told, first of all, when those beginning and end points were for each regime, inflationary, disinflationary. Let's say you have a two-state model. And you'll also be told how that process works, right? So regime switching model will use what's called an autoregressive process, which essentially means the data has memory going back to certain length, and we're going to make use of that in a second, okay? So at the very least, now your folds are taken care of. You can actually, okay, I get it now. I split the world, first of all, into, let's say, 5 inflationary regimes and 8 disinflationary regimes. Let's split those two into 2 halves, first of all. Now, I'm going to take my inflationary regimes and use part of them to train, and then part of them to test and validate. And I will now see how my model works in inflationary regimes, which have economic meaning now. If you buy into, let's say, a Hamilton or a Falardo kind of regime switching model, which I think have merit, right? By the same token, you can go to the disinflationary data set and say, look, I'm going to bring that into the foreground now, and I'm going to actually now train on one set of folds, if you will, and validate and test on the other disinflationary folds. Then you know, first of all, the regime switching model has done 2 things for you, which are very important. First, it's the number of folds, but second, it's actually dissected and cut up and classified the folds into economically meaningful buckets. And that's very important for us because we don't want to, first of all, discard a model because it works. Maybe our strategy works great in inflationary environments. It doesn't work great in disinflationary environments. We want to know that because maybe we can retain that and report to our colleagues, our stakeholders, and senior management. Guess what? You know, maybe it doesn't work all the time. It's not an all-weather kind of strategy, but you know what it's really effective in? Inflationary regime. So you always want to try to get a takeaway from your model. It's hard work that you're putting in, and there's one way of doing so. So it tells you, first of all, how many folds, and then it gives you economic meaning to those folds. Now, there's another sort of a minor point that is important here, which is that when let's say you have your folds organized and you got, okay, I've got my training and my testing and validation. It's often inadvisable in traditional data science to just have your training set end, let's say on observation 100, and then have your testing and validation, let's say start on observation 101. Why is that? Because in some kinds of data, like time series, financial time series, data has a memory, right? So that data point 101 actually remembers, and 102, 103, those early data points actually they remember kind of what happened in the training period. So there's a risk of polluting that testing and validation data. And while it's not quite overfitting in the traditional sense, it has that sort of cheating with a small c connotation to it. So what has been advised in data science has been to use what's called blocked time series cross-validation, where you drop out, or if you use scikit-learn, it's called a gap, right? The way they do it, I think. You basically leave out some observations between the training set and the test and validation sets, so that the testing and validation sets forget, if you will, what happened before. Now, the question poses itself, well, how do you decide what size that block, that gap should be? Again, traditional regime switching gives you an idea, because every regime switching process has a data generation process. It assumes autoregressive process, AR1, AR2, AR3. That value for that AR process is the logical choice, because that essentially tells you the length of time it takes for that time series to forget. So by putting the AR size in between training and test, you get an economically and statistically coherent way of deciding what block size you should use between these two types of folds. Okay, so there you go. There's an example. Now I thought of this on my own, because I was thinking, for years, data science itself doesn't tell us how to do this, because they don't care about finance, right? They don't care about financial time series. Traditionally machine learning scientists and data science and so on. So there you go. There's one respect in which econometrics actually plays a potentially invaluable role in making our validation process more robust. Hence, there's good evidence, that's good evidence, it should be used. Okay. Now in the paper, I do another thing, right? So I say, look, I use with the fundamental law of active management, which you may not know what that is. Here it is. So it was introduced by Grinold, and it's basically a way of analyzing an active manager's alpha generation process. And this is a variation on the original by Yi, 2008. The reason I like this articulation of it is because it has this uncertainty parameter, this variance of the information coefficient. The information coefficient, simply put, is essentially the predictive correlation of your signal and the actual observation you make, T+1 or T+2 or whatever you're looking at, right? So the idea is that it actually measures the predictive efficacy of your process, or if you're analyzing an individual model of that model, okay? And you're trying to get as high of IR as you can. There are different ways of articulating. The reason I use this in the paper is because it actually lends itself to a couple things. So N is the number of bets or views or signals that you have in the model. You can interpret that number in different ways. So what we do in the paper is essentially we use this cross-validation process that I just described based on regime switching to get us the IC number, to get us that predictive score. In other words, we build a model, right? And I build some toy model in the paper. Very simple. And then I say, okay, let's cut the world up using regime switching. And in each of those regimes, run cross-validation and try to get some sort of understanding of what the predictive effectiveness of each of my features or factors is. And I use Fama-French. I use a very basic model, right?
And your model is about predicting or estimating growth rates, or about classifying? What does the model do?
Well, it classifies, of course, the first module, the first step. And then in the second step, we want to do two things, right? We want to say, so each of our factors is what I consider a view, right? Because let's assume you're just trading on, it's simple, right? It's a toy model. What the value factor is doing today, to simplify it, what is the value factor's return today? Does that tell us anything about, let's say, the return of a stock tomorrow?
Okay. And so it's a predicting the return of a stock, or maybe
yes, exactly.
a up or down classification?
Yes, predict the return of a stock based on a signal, and that signal is simply the T-1 or time T value of a factor.
Yeah.
Because it's just to illustrate it. It's not something I would use in practice, right? Obviously. So according to this articulation, or even the traditional articulation from Grinold of an information ratio, that IC score, that predictive score, is only one input into getting a sort of a information ratio. The other is the number of views you have. Now, you may say, Joe, that's simple. Just count the factors you inputted in and go from there. But there's always the risk, right? Remember our old lessons from OLS regression. There's always the risk that our factors are correlated to an unacceptable degree. If they are, then that they would not count or qualify as independent ends, right? They'd have to be considered the same signal in essence. So what the second thing I do is I use a machine learning very simple machine learning clustering algorithm, affinity propagation. I'll tell you why I picked that. To tell me, okay, I've got 4 factors or 5 factors. Now look at their various characteristics, time series characteristics. Are they the same feature or factor, or are they different? And that will be my actual end that I input into this information ratio calculation, right? So this is a way, instead of just measuring their correlation, it's trying to get a little bit deeper by putting a few more characteristics or qualities. You can put many more, actually, if you want, right? Sky's the limit. And the clustering algorithm will tell you, what the actual number. And so what I got in the paper, again, a simple toy model, I had 4 signals. And after this operation, it told me that there's really 2 factors, the market and everything else. In other words, all the other Fama-French factors, and in terms of the period I looked at, were put in the same cluster, okay? Now, I have a disclaimer in the paper that don't take this as some sort of authoritative statement on these factors in any respect, because it's a toy model. The whole point was to give a very simple application and tell you what this showed us, right? It could be because the selection of the characteristics for the factors was different than somebody else would use. It certainly doesn't speak to the Pearson correlation between these factors, which is shown to be low enough to actually, qualify to be put into regression. So in no way is it trying to argue against the Fama-French model. What it's trying to show you is that if you use this clustering technique, you may get different result than you would otherwise. So again, every application has to have its own approach to this question. Now, the reason I used affinity propagation is very simple. One, there was 2 reasons. One was that it's a graph theoretic technique, so it's easy to visualize if you had to, the relationship between clusters and so on. But the main reason is because, unlike other clustering techniques, affinity propagation will tell you the number of clusters. So you don't have to posit number of clusters. Now, of course, there are other ways of, like, if you can say, oh, let's just, let's say in spectral clustering, for example, which I've used before a lot. You could say, oh, let's try with 4 clusters and 5 and 3. And there are these tests, silhouette scores and all these other kinds of scores, RAND index, that you can apply to each of the clusters to tell you which of them is more robust and which of the schemes is what you should. Oh, this is the 3 cluster scheme is actually the most robust out there, right? But I use affinity propagation because it actually tells you the number of factors, the number of clusters, excuse me. So it's a convenience that it provides. Okay. So that's the model, and the whole point of this, and here's the references for everybody's perusal. The point of modular model validation was to say, look, there is a natural place for traditional econometrics in producing the inputs into what ultimately ends up as being a cross-validation or a machine learning-driven validation process. Now, I want to caveat what I just said by saying this paper and this framework is not the only way to use traditional econometrics and machine learning and data science together in model validation. It's just one example, and one that where I'm saying that they can work naturally together. You don't have to force the issue, right? But I definitely recommend others to work on this and say, well, look, how can we combine traditional statistics and more, let's say, cutting edge or novel techniques in order to validate our models better? Because each of the frameworks has a lot to offer. Like I mentioned, things like regime switching and other kinds of econometric models are very rooted in economic assumptions, economic processes, right? They've spoken to these things for decades and done a lot of research on them, and it's all good research. So it's not necessarily overturning anything. Data science and machine learning have been focused on a completely different area, which is just, to a large extent, classifying things, seeing patterns in things, and then predicting, right? So while the 2 areas are not mutually exclusive, their priorities are definitely different. So with that, I'll end the formal part of the presentation. I'll go to the questions and
Yep, so I've collected 4 questions at this point.
okay.
So let me start sort of with the first ones. All right, so the first one is first it starts with a compliment. This is such an interesting talk. And then they ask, how does modular machine learning facilitate model interpretability and explainability? And how does it impact model scalability and efficiency, especially in large scale scenarios? So I guess they're asking about interpretability and scalability.
Well, so interpretability, it's clear that when you are cutting up folds using some kind of economic criteria, one that is very rigorous, like a regime switching model, that is, a leap from, arbitrarily picking folds, right? Because you can actually explain why did you cut the world up into this many pieces, right? Subsamples, right? Folds. And and what are they? What is the economic flavor or character of these subsamples? So that goes a long way in a sort of an internal presentation, if you will, because people will say, "Oh, I get it. This is inflationary. That's growth. That's contractionary." There's different regime models you can set up. The other way that it can is on the clustering side, because you may have a lot of folks, including many quants, who may say, okay, you have this model, it's got X number of features or factors. Are they in fact different? And when you use various clustering techniques, you may come up with results that can answer that question. Well, initially we thought they were different. Now we found out 2 of them are the same, but the other ones are in their own clusters, or whatever the answer is. But that operation itself aids in this effort to explain the model better. Now, scalability, I think it's more on the second half of modular machine learning, where, again, the clustering can potentially help, dimension reduction, right? Because, you may test the IC scores, right? You may do the predictive scores for, let's say, 50 signals, 50 features, and they all come out very strong. You may on the various tests that you have, right? But then you throw them into a clustering scheme and you find out that, okay, look, these are, 10 of these are the same. And then you can basically whittle down again your set of signals to ones that are the most effective and also, are distinct, right? So you may have a sort of 2-headed criteria. I want to have a signal that is, very distinct, but also has a very strong IC, and you may have different weights you put on each of those criteria. But the whole point is you can actually help narrow down a larger set of signals. It's kind of a distant cousin, although not mathematically necessarily the same, but in spirit, it's a distant cousin of lasso, right? Where you can take a bunch of factors or explanatory variables, and then and say I want a feature set of 8, and lasso will cut off the ones that have basically, it will leave you with the set that have the most predictive power, but simultaneously are also the most least correlated with each other, right? I think the one advantage of clustering, though, will be that lasso operates solely within a regression framework. Clustering can actually include many different kinds of characteristics on your signals and make the distinctions that way, right? Like I said, my example, if I put in other criteria, you may have gotten different results, right? So, it was a toy model. Don't put too much stock in it. But the procedure can be used effectively, no matter what scale problem you're working on.
All right. So our second question is, to what extent does one need a model like Markov switching in recognizing regimes versus just using regimes one knows from experience or intuition? And I think the second part is related. What are your thoughts on quantomentals? So I suppose that's maybe another way of phrasing this idea of you combining intuition in order to do this cross-validation.
Yeah. So the first question is, I recommend you, I'm not just talking my own cooking here in my own book, really read this Minsky versus machine paper, because what I do at the end, so in the beginning, I criticized like Hamilton and Filardo models, which I use for other purposes, obviously, right? but I criticize them for their predictive effectiveness. And I also criticize people on Wall Street for pretending they use regime switching models when they don't, right? And it's not just me, right? I told you, Engel and many others have talked about this for years. So the main point of that paper is to use a spectral clustering, actually, to forecast regimes. So I actually do that in that paper with my co-author, who was an analyst at the time. We basically depart from a traditional Markov switching framework and just use spectral clustering straight away. At the end of that paper, though, what I do is I go and I look at the NBER, National Bureau of Economic Research. They have a very heuristic way, right? They have a committee that, after the fact, looks back and says, okay, we're going to classify these years as expansionary, these years as contractionary, right? So that's a completely heuristic or lived, lived experience approach to regime classification. And we compare our classification results with NBER, and we find, I believe, that they overlap around 70% of the time. So it's not that as if any of these schemes is going to have wildly different results. Our concern in the paper is really, let's have a significant material improvement over the predictive effectiveness relative to traditional regime switching models. Right? Let's actually build a pretty sophisticated toy model and really robustly test it. I'll tell you how I tested it in the paper as well. It's interesting for this crowd. And then we'll get our results, and then we'll compare it to an NBER classification. And we assume that there's going to be some overlap, right? So it's going to have more or less traditional regime classifications, but the advantage it has is that it's predictively much more powerful. So one of the things we do in the paper is we don't just do a back test, out of sample, and across validations. We do those. We also resample our time series. We do what's called bootstrapping, which you may be familiar with, right? So we use something called a stationary bootstrap. So what we do is we create 200 synthetic histories, and then we out of sample cross-validate the strategy in those synthetic time series also. So that's another layer of robustness. I haven't a lot of time to talk about this today, but I think a big part of model validation has to just not to use historical data, but to also utilize synthetic data. And that can be a Monte Carlo simulation, which is I don't do as much anymore. It can be bootstrapping, which I do heavily. I use a lot, or it can be the use of things like GANs, generative adversarial networks, right? Which are a new kind of a newer kind of machine learning technique that can be used to generate synthetic data. I would definitely test all of the strategies that I come up with, or anything I devise, I'd validate using not only actual history, but synthetic or resampled data as well. Because that's a good way of, again, trying to break a model. And if you can't do it with these techniques, then there's a good chance that, a decent chance that you've got something there. Now, you may say, Joe, why would you do that? And think about it this way. Finance is actually very data poor relative to natural science, if we think about it, right? Because if you think about, let's say, drug trials, they've got literally minimum 50 life histories that they can analyze. So their sample is, they have like 50 S&P 500 histories. We have one, right? If you look at a drug like COVID that was released to the public, they literally at this point have maybe billions of histories that they've looked at, where the next generation of COVID vaccines can be informed by. So in finance, and you can't, in our business, you can't say, oh, well, use the Russell 2000, it's the same thing, or 1000. It's not the same thing as S&P 500, it's different, right? And whatever, in some respects, it's different. So we are data poor. So just using a historical backtest may leave you open to model failure when you're presented with a new set of data that the model hasn't seen before. This is a classic overfitting problem, which is very hard to overcome in our business. One of the ways you can try to is via using synthetic data in various respects. So I'm a big proponent of that idea.
Okay. The next question we had was about, and so maybe your Minsky versus machine paper and the modular machine learning for model validation paper, we could put some links on when we post the video, and hopefully because someone else was asking about whether this modular machine learning paper is sort of available outside of a paywall?
I don't think so, but let me. I don't think it is. You can check and then just reach out to me if it's not.
Okay,
If it, yeah.
sounds
I want to. Let me just give you the link to Minsky versus Machine.
okay. And I'll let me know when you're ready for the next questions because they're starting to
Okay. Yeah,
avalanche over
no, you
here.
can go ahead. You can ask me. I can do.
Okay, so yeah,
I can do primitive multitasking.
so I'll the next one was about they ask in traditional machine learning models, the train test split is typically an 80-20 split. And so the question is, in time series models, you said something about cutting into sub periods and with blocks in between, and I guess they were asking about a little bit more detail about how that works, this train test splitting in a time series model.
Well,
That
in the modular machine learning framework, the regime switching model tells you how long the regimes are. You just go with it. Hopefully, the sample size is large enough to be, sort of appropriate or legitimate, if you will, right, for statistical analysis. It usually is, right, especially if you're using weekly data or daily data, of course. But on the 70 or whatever it was, 70, 30, 80, 20 split
20,
idea, what I would typically do is I would actually test it on different split values, have a spectrum of splits, and the model hopefully will perform well no matter how I train and test. Obviously, if it, for me, the danger always is if you train on a smaller sample, a subsample, then the first blush you're thinking, well, that's better because I trained with very little information, was able to generalize very successfully. But then I always think to myself, but maybe that's some sort of statistical luck, if you will, or what have you, right? And so, but then obviously, if you use too much to train on, then there's an overfitting issue, and then there's just a practical issue. You don't have enough data left to actually test your model on. So what I do is I try to pick some reasonable values and just go down the spectrum and try to look at what the model does on each of them, and then if it's successful across the board, then that's a good indication of. But that issue is much less important for me typically than picking the correct folds, right? And that's why I think the regime models are helpful in that they let you pick economically meaningful folds, right?
Well, it seems to me that in finance we often work with moving windows, right? And sort of we think of after all, if a model is in production, it's always going to train on past data and then predict over the course of, let's say, a day or a month or a week, and then there will be a retraining. So I kind of feel like when you backtest, maybe using moving windows seems like the way to go rather than your ML, train test split.
Well, it's an interesting point. I'll tell you something so I wrote a paper with some co-authors at a prior firm. I won't mention them now. No, I still have friends. It's just I don't get paid, so why would I mention their name? But and what we did in that paper is we started to talk about, this paper was not a machine learning paper, and it was designed for pension plans. We wanted the pension individuals to really read this paper. It was an LDI paper. And one of the things we did in that paper is we picked rolling 5-year windows to test. So those are essentially like our rolling folds, right? In other words, you take each 5-year period as your testing period, and then you figure out how does it do on each of these. Now, why would we do that? Aside from the reason that you mentioned, Sasha, sometimes you have to speak to your client audience. Pension plans typically do a 5-year review. So a pension committee will typically look at things every 5 years. So if you're consistently doing well, your strategy doing well on these rolling 5-year windows, that's a good indication that in a realistic setting for a pension plan, the ideas that you're advocating, this is a toy model, but we're trying to advocate a particular idea, right? Not so much a particular product or a model, but our approach works because it's actually working on these rolling 5-year periods, which you, the client, deem important for your business operations. So that's a good point, and I think that you want to look at things in a lot of different ways. There's no one way of looking at it. So here's a simple other thing you want to look at: inception points. So you've also all seen those charts where, okay, the performance of something over X number of years is very good, cumulative returns, growth of $1, right? But then you move that starting point backwards or forwards a few months or years, and the whole strategy collapses, right? Now you have 80 cents on the dollar 10 years later or 20 years later, or whatever it is. So even moving this inception point window, these points where you're measuring the growth of $1 or these kinds of cumulative return calculate is important, right? Because you don't want to lie to yourself. That's essentially what I'm getting at. You don't want to cheat yourself, because then eventually that strategy is going to be put into production and it's going to fall on its face when the exact conditions that you used to build the model don't materialize. Things change radically. And so it's better to be honest with yourself and say, look, it's also like when I see sharp ratios of 8 and 6 and things, there are ways of juicing strategies to do that. Massive amounts of leverage, obviously ultra risky positions, but over time, those mega sharps will dissipate, right? It's just statistically, they just can't last that long. Because if you're exposing yourself to that much risk or that much leverage, typically the tide will turn against you. So there's all these statistical smell tests that I call them, right? And you have to think about it in the following way. Investing is hard. Whether you're a fundamental manager or a quant manager, it's not an easy business, right? That's why the great investors of all time are well known, and we learn lessons from them. I used to work for a number of them. Somebody like Bill Gross, who is not a quant, but I think he's a brilliant person, and learned a lot of lessons from him on how to invest and approach the markets. And if those people were right 55% of the time, 60% is you pushing it, you're going to do very well in this business. It's literally those are the kinds of numbers we're talking about. And you can forget about 80%, 90% out of the park. That's not realistic. So when you're developing models, you have to have very stringent criteria, to make sure that you're not even inadvertently lying to yourself, right? Mm-hmm. If you are, you got to go back to the drawing board. That's just how it is, right?
So we've got we're a little bit over time, and I think we have 5 questions. And this is what I suggest. Maybe we could do 5 questions in 5 minutes kind of thing, a little bit of a, and if the question is just a yes or no question, then we move on to the next. That way, everybody that, I have to say that there's been a lot of more questions than we're used to. So that's all credit to you. So, all right, question number 1. Are we saying, so affinity propagation, you mentioned it before. Is this a model that does not impose a number of clusters as a hyperparameter to tune in your data set?
Yes, it tells you how many clusters. Yeah.
Okay, great.
I just posted Minsky versus machine.
Okay, perfect. Okay, so then the next question is, the implication for the traditional fundamental investing is unflattering, right? i.e., the common assumption that the fundamentals drive stocks work only at long term and not even all the time. Well,
let me put it in a different way, and I'll do it in a minute.
Sure.
It's not that the fundamentals don't drive. Our business is finance, so there's got to be some economic intuition, right? The inputs, the features, what have you. But I think the implication for a PM who thinks me and 5 research analysts are going to conquer the world in 2024 is very difficult to do, because there's so much information, so much data coming at us, that without using quantitative tools in a robust fashion, I find it implausible that you can succeed as an investment manager. There's got to be a fairly deep integration of quantitative methods now, even in fundamental teams, or I think they're going to lose against, better armed, if you will, opponents.
Okay, then we have someone who made an interesting sort of synopsis of your approach. He says, and I guess it's going to be am I right, or is this the right, did I understand this correctly? So he says, you gave 2 examples, one of which is regime switch, and which actually helps you split your data into train and test periods. And secondly, you use a machine learning model tool like clustering to reduce dimensions, and then you use an econometric tool. So you're using both tools. Am I right?
Yeah, exactly.
Yeah. All right. The next one is, okay, so are there known examples where econometric methods might help explain the predictions that more opaque machine learning models make, especially for a situation where machine learning algorithm performs better with predictions than the econometric model?
Yes. So I have a paper coming out soon with my friend Paul Billicon, who you may know from Thalesians and Imperial College London. It's not out yet, but it's going to come out in Journal of Financial Data Science, and it's called From Deep Learning to Deep Econometrics. And this paper really hybridizes the two frameworks to predict volatility. So this kind of goes into the questions that you're asking right now. So look out for the paper. I think it will answer some of these questions.
Okay, and I think this is a good last one. In your opinion and in your experience, can machine learning algorithms ever give out a prediction with a large accuracy and minuscule variance?
No, I think it's a trade-off that we're constantly dealing with. And it's just I won't say it's analytical or it's a tautology, right? But I think it's at least near impossible, right? I think it's a trade-off that is inherent in what we do, and it actually encapsulates in 30 seconds. I could say that's the basic issue, that machine learning models have emphasized the generalization, right, at the expense of the explainability, and econometrics models have done the opposite. So that trade-off, the two cultures, if you will, have taken different sides of it to prioritize. And I think that's why they're both useful, but I don't think we can get away from that and sort of find a unicorn that satisfies both priorities equally.
Okay, well, Joseph, the last question is just a comment. Thanks a lot for this fantastic talk, and I guess I second that emotion.
Okay, thanks for everybody. Thanks for having me. Good luck.